of Physics. He did his PhD from IISc Bangalore, then moved to US to do some high performance computing research activity. I'm not authority to talk about in detail what we discuss with us. So let's hear it from Honest Professor.
Thank you, sir. So I want to have a little show of hands. How many people listen to music and like music? Everybody. How many people play music or do some music in their as a hobby, either singing or playing some instrument? That's also included. Anybody who hums or taps the desk is also included in there. Okay. How many of you in your life ever wanted to play some music but couldn't because of studies and other activities? I think that is also so. Music is in everybody, but because of some situation we are not able to explore it. So my goal is to allow anybody and everybody to get to that point so that anybody can explore it. And don't listen to me, like listen to our icon, Albert Einstein, who said, if I were not a physicist, I would probably be a musician. I often think in music, I live my daydreams in music, I see my life in terms of music. I get most joys in life out of music. And he was a very established violinist and he loved playing violin. So there must be some relation between physics and music that Einstein was so inclined towards. And there is enough evidence, scientific evidence, that shows that playing music has a lot of benefits to us. It engages every part of the brain. It enhances memory. As you can see in this diagram, this is from a Nature paper. The act of playing a musical instrument, it develops your muscle, which you use to develop fine motor skills to play an instrument. The sound output of that instrument goes into your ears, and your brain develops, and you get entranced into that activity of playing music. And I want everybody to have that benefit. Like playing music is effortless, but getting to a point of playing music at that skill level, like these people are totally like completely in a meditative state when they are playing the music. Getting to that state is very difficult. One, you have to pick an instrument, then you have to find a teacher to teach you. You have to practice that instrument for hours every day, and you have to do that for several years, and you have to play in front of an audience many, many times. Then you will get to that level. So I want to reduce all of that effort and give the benefits of the health benefits of music to everybody. Which is why I developed this software called QwertyZen Community Edition, and it's a new musical instrument that anyone can use because everybody has a laptop. The software itself teaches you, guides you through experimentation, and it will enhance your creativity and agency. And the idea is that I want everybody to have the benefits of that musical practice. Right? So today's talk is about music, and all of you are like scientists, like either physics or chemistry. And first I will ask, is music invented or discovered? And we can easily say that it's basically sound, so it's discovered, or it's a language, so it's invented by humans. But the answer is not so obvious. Firstly, there are aspects about music that are discovered. If you strike a string, the string has vibrations and modes of vibrations. That is a source of music. I will explain how. The harmonic series of that string, the timbre, the sound of every different instrument is different. The consonance and dissonance, whether a sound feels good or it feels jarring, that is discovered within our minds. Rhythm can entrain us, it can influence our heartbeats depending on the pace of the music. That is also discovered. We have not invented that. Psychoacoustic effects, physiological effects, these are all real. That happens because of the sound that comes into us. The parts of music that are invented, we have invented the scales, the tuning systems that go into the to define what music is. The music theory has been defined by humans. Musical instruments have been invented by humans, various instruments like piano, violin. The genres, the culture that grows around all of that music, and also the written language. So, how do we, the part of music that is discovered, if you have a string that you hit, you get all these modes of vibration. And I'll play the sound of the first 16. Is that audible?
Very faint.
So those are the first 16 modes of vibration of a string whose fundamental is 256 Hz. That is named as the C note, and that's the fundamental of the string. And above that is the octave, which is the first harmonic of the note. You get the perfect fifth of that. So, and this column shows the relation to the fundamental of the string vibration. And you will see there is a 3/2 which is called perfect fifth. It's named G. There is again we get the octave. You get the 5:4 ratio to the fundamental, which is all the major third. These are names that have been given to these frequencies over many years and evolution of the musical system. So today I want to talk to you about how these names happen, what is the relation of these notes and these names. But ultimately these are only frequencies and pitches. And this is one aspect of music, right? The notes. In this series, you can see that there is a perfect fifth, third, fifth, seventh. There are names like C, G, E, G, B flat, whatever. But some of these notes do not exist in this harmonic series, which exist in musical scales. So those had to be invented. For instance, the F note does not exist in that series. But we know from music theorists that the F is the perfect fifth of, the C is the perfect fifth of F. We know the perfect fifth is a 3/2 ratio. We know what the C is, so hence F is the 4/3 of the C. We also know that the F, the G is the major second of F. From that back to the table, there was a major second which is 9:8. So G is also the major second of F. We can derive the F from that. Both of them 4/3, that matches. And we can derive all the notes from the vibrations of a string. So we can say that the notes are not invented, but the notes exist in nature. These are the musical notes that we use in musical compositions, and it's not what humans have invented, but we have acquired. Next, music is a language, so it has formal grammar, it has rules and constraints. Humans have invented this. I'm not going to explain to you what this is. This is how tabla practitioners talk about the rhythms, and this is what Western musical people write their music as. We will not talk about this, we will talk about more about how to think about it in musical or scientific terms, what music is. So first, music is, you can consider it's just a waveform, is a function of time, and though that waveform, when it hits the speaker membrane vibrates, that vibrates the sound, air, and those pressure oscillations hit our ears and we hear some sound. But what is the difference between noise and music? We have to distinguish between that. So we have to say what is music and what is not noise, right? So you can say music is a combination of two different or n different instruments, and there is some periodicity involved in that, in those. So we can say it's a sum of several functions of time which gives us some ultimate sound, and that is music. But that is also not enough. Like, there can be periodic noise. So we have to go further into the abstraction about what is music. And so we can say music is a sequence of note vectors. each note is some vector and the note is defined by some parameters. The parameters include what? The note has to have some time at which it starts, and that defines something called rhythm or beats. The note must have a note value, some pitch or some frequency, which is shown over here in the x-axis. The x-axis is the time axis, the y-axis is the pitch axis. It has some other properties like the source or which instrument it is coming from. The same frequency, the same note produced by different instruments sound different. So this is where I will introduce to you the software.
Some parameter is also involved in the amplitude. Is only
Yes, the note velocity, which is the force with which we hit the either piano or guitar string. That is the amplitude. There is also a note duration. So how long the note exists, how does it decay or does it sustain? And you can also have expressions like, is the note bending, is it sliding, is it vibrating? So and these are the basic properties of a note, but there can be further properties. So you can think of a note as a point in a vector space of some dimensions. And then the music, an entire piece, you can consider it as a sequence of those vectors. So,
so these are the, you're thinking of, these are the elements of some vector space?
Yes.
Like that.
Yes.
And linear vector space.
This is how computers express music as internally. And this is how they compare, like if you go to the software to compose some music, internally this is the representation. So we looked at music as simple waveforms, but then waveforms can also be noise. So how do we discern between noise and music? So there is something called quantization and periodicity. And we'll talk about a few concepts to get us to that point, right? So as we saw in the previous graph, we have in the y-axis the pitch and x-axis is the time. And you can see it is quantized in the pitch axis, also quantized in the time axis. There is some periodicity involved.
The quantities or parameters that forms this vector, a vector of a vector space or something.
Yes.
So is this space, I mean, these are linear? Or
Yes.
Okay.
So it adds simply to produce the sum of the sum of the whole is just a simple addition of these. Let's talk about a little bit of mathematics about how notes happen. Like we have derived the notes from a vibrating string, and then there are some rules of what these notes can be. So everybody knows what the 7 fundamental notes are, and it's known as the Saptashur, and these are the alphabets of music. So everybody knows the sa, re, ga, ma, pa, tha, ni, sa, right? Let's see. Okay. So this is sounding from a piano. When I say the timbre of sound, these are the notes. If I change it, the Saptashur from 2 different instruments. So the notes are the same, but the quality is different. Whenever we hear it, we know that it is being sounded from a violin or a piano or a guitar. But the sound, but the pitch is what is constant. Right? Now, this is the same as in the Western solfege system, do, re, mi, fa, sol, la, ti. And it's amazing that both of them, even though from ancient times had no relation between each other, came upon the same set of 7 notes to play the same music. Got rid of all this system and come to a system where the notes are denoted by C, D, E, F, G, A, B, C. Right? Now, this what you said about identical system is like these are named pitches. Right? They can be anything like 256 Hz, 440 Hz. The sa can be any pitch. But now it has been standardized using these names, and C is something like a 256 Hz, and it's octaves. And in our mathematical system, we just call them intervals and give them numbers 1, 2, 3, 4, 5, 6, 7, and the 1 is the octave. Right? And then we forget about what the names are. But the names have meaning in the Western tradition as well as in the Indian tradition. So 7 notes are not everything. There are more further notes than that, and there are some holes in this. And what are those gaps? There are some gaps in between. You can see between the E and F, no gap, between the B and C, no gap. But there are 5 different places where notes exist. So in the number system, they are called sharps and flats, like 1 sharp and then 2 sharp. So the sharp is an operation that says, okay, the one note higher than the previous. The flat means the note lower than the previous, right? So that is used in both the modern system of this was C sharp and B flat, and those are the same note, the same pitch, the same frequency. In Eastern tradition, they are called the Komal Re or the Tivrama over here. And this is exactly reflected in the way piano is designed or the harmonium is designed, where the white keys are the natural notes and the black keys are those accidentals, which are the sharps or the flats. Okay, now C, D, E, F, G, B, C, that is our Sarigama Padhanisa. There is 5 extra notes. What happens with those? What is the meaning of having extra notes? One point I want to get to is like, okay, now that we have a scale, how many possible melodies can there be? How many songs can there be? Right? That's a question I want to ask. So let's assume that we have 8 equi-spaced note sequences, that is the rhythm. Okay, we keep that constraint. And there is some pattern of selecting those notes that gives us the Sarigama Padhanisa, right? The C, D, F, G, A, B. If we move that pattern around and construct the major scale from all other starting notes, you see that we get this kind of pattern. Like that is your Sarigama Padhanisa starting from C. That is also Sarigama Padhanisa, but now starting from G. That is also Sarigama Padhanisa, but starting from D. Now your note names have changed. So you have to, if you are playing the piano, you have to understand that now you are including 1, 2, 3, 4, 5 white notes and 2 black notes when you are playing D. So you have to reorient yourself and play the same Sarigama from the. Why do we have so many different things? These are, remember, these are only pitches, just hertz, just frequencies. But this aids in like, female singers and male singers have different vocal registers. Even among different people, they sing at different pitches. So this aids different singers to perform the same piece in their own vocal ranges. And that is why we have so many transformations. 12 different rotations or transformations of the major scale. And all of these are the same, Sarigama Padhanisa, right? Another kind of transformation we can think about is rotating the major scale. So the major scale, as I said, we can consider as numbers only, 1, 2, 3, 5, 6, 7, and 1. The major scale is very simply all the natural notes. If you look at the A major scale, the same Sarigama Padhanisa but starting from a different note, we get all the note names change. A, B, C sharp, D, E, F sharp, D sharp, A. It's still the Sarigama Padhanisa. Right? What happens if the C major scale has an A? What happens if we rotate the C major scale starting from an A? Right? We get this different scale, A, B, C, D, E, F, G, A. It looks the same, but I want to let you hear how it is different, okay? So here you can see, this is right now the C, D, F, G, A, B, C. Right? It sounds. Right? If I show you what the A major scale sounds like, you can still recognize it's the same Sarigama Padhanisa, right? But if I go back to the C and now rotate it to start from the A, right? Now it starts from the A. Suddenly what sounded happy now sounds a little sad and melancholic. You feel that what was happy has become sad, and that is because the relation between the notes have changed. It's not the same formula anymore. Before you had 1, 2, 3, 4, 5, 6, 7. Now if you see, from the 3, we have to lower the third to get the flat third. We have to lower the 6th to get the flat 6th, and you have to lower the 7 to get the flat 7. And the entire relation of the notes to the tonic has changed. Sorry, I should not be pointing this around. Has changed, which results in different feeling. So now we have.
So why do you call it rotation? With rotation on a ring kind of thing.
Yes, so you can consider the chromatic scale as a modulus 12 group, and you can have like operations like first. So from that group, from that set of 12 notes, you select 7 notes, which forms your scale, right? And now you can have transformations like you can transpose the note so that you have the same scale moving around, or you can have the rotation, which is like you're starting from a different note on the same set. So I just took the C major scale and I produced 2 different feelings, a happy and a sad. And that is like when I rotated from the 6th. Now you can imagine there are 6 different rotations of the scale, which will give us, this scale is called now the A minor scale. A minor scale is the relative minor of the C major scale. Every major scale has a relative minor, and the minor scale has a sad dark feeling. And now we can say that there are 7 different rotations of that major scale, and they have 7 different feelings. Okay. Now these were discovered by the Greeks, that is why they have like very Greek sounding names. So the first, our normal Saridamapadesa, they called it the Ionian scale, and it has the normal modes, and it sounds happy and bright. I'm going to demonstrate this in a very short way. So I'm going to keep the C as the tonic so that our ears can say it with the tonic. That's the happy major sound we all know. Okay? Let's go to the second mode. And we're in the Dorian. Dorian has a jazzy, thoughtful feeling. Okay. How does that sound? Totally different feeling from the normal Saridamapadesa. It's quite uncommon, so it feels very new to us. But jazz uses it a lot. People who listen to jazz are very familiar with this sound. Listen to this, okay? You will be very familiar with this. Dark, soulful, and it has a relation with the last hair. Okay, and the Greeks called it the Phrygian mode. Then you have the Lydian, which has a very bright tone to it. And you can see the Lydian mode starting from the C has the F has been sharp. So there's one sharp. The only difference from the normal Saridamapadesa is that its 4th note has been raised 1. It has a very Indian music feeling as well. Then there's the 5th mode, which is called the Mixolydian, and that has a bright, happy feeling similar to the normal scale. But except this note is like flattened. Bright, happy feeling. And then there's the Aeolian mode, which is the sad, back to the. And you can see the software makes it very easy to explore all of this. Okay, and the last mode is the Locrian mode, which is very unstable. It has all these flatted notes. You will understand the moment you hear it. It has no stable point. No stable point. It does not resolve anywhere. It's very unstable. It does not feel. It wants to go away somewhere. This was a small demonstration of the rotations of the scale. Okay, this software is actually a live performance system. So imagine that you have like 3 people with laptops. You can play them like an instrument or a band.
What is the price of the?
This is free. You can download it for free completely. Go to my website, QwertyZen.com. I would really like your feedback on this if you download it.
Thank you once again.